Do people starting to tune in? I am just sending out the link on Remind. We're getting started a little bit early tonight just because I feel like it. And yeah. So just give me a sec and we'll get started. To all my classes, third block, fourth block. We're live. All right, on the agenda today is finish up bonding and do some periodic table. Maybe we'll get into IMFs as well. I might push IMFs for tomorrow, just like a review of physical versus chemical changes. Do IMFs tomorrow, but we'll see what happens. We'll see how we feel. All right, so polar versus nonpolar. So a word that's going to start coming up a lot right now and this whole video is electronegativity. And while you can look up the values for electronegativity on table S, it's also important that you know what electronegativity is. And that's the attraction for electrons. So how strongly does an atom want to attract an electron determines what their electronegativity is. And it ranges anywhere from non-existent, so the noble gases, group 18 on your table S, won't have any electronegativity values, but fluorine has the highest at 4.0. But what I'm mainly going to focus on tonight, right now, is polar versus nonpolar. And there's polar bonds and nonpolar bonds, and then there's polar molecules and nonpolar molecules. They're not the same. So, a nonpolar bond will have an electronegativity difference of 0. Meaning, the only way you're going to see this, most likely the only way you'll see this, is if the bond is between the same type of atom, meaning Cl2, N2, etc. That's pretty much the only way. There's very, very, very few atoms that actually have the same electronegativities. So the only way you're going to see a nonpolar bond is if their electronegativity difference is 0. And what do I mean that their electronegativity difference is 0? So if you go to table S on your reference table, and let's say you were doing Cl2, the bond in Cl2, you'll notice that its electronegativity is 3.2. So, when you have chlorine with chlorine, let's draw their dot structures here. This electronegativity is 3.2. That one's electronegativity is also 3.2. And when you subtract them, you get 0. So we consider that a nonpolar bond. If all bonds are nonpolar, molecule is always nonpolar. You can't have nonpolar bonds and be a polar molecule. That doesn't exist. So if you have all nonpolar bonds, you will never have a polar molecule. Never. You just won't see an example of that. Period. I'll just leave it there. So in any atom that's bonded to itself, you know, O2, F2, N2, these are all nonpolar bonds, nonpolar molecules. All right, polar bond. Two different things. one. Two nonmetals, because usually once you throw a metal in there, we're going to call it ionic. And their electronegativity difference is somewhere between 0 and 1.7. And that 1.7 I think is kind of arbitrary, but that's how we typically define it, between 0 and 1.7. So, for example, if you look at HF, and you go to table S and you look up their electronegativity values, H is going to be 2.2, and F is going to be 4.0. And this is why I say, of course I pick one. This is why I say that 1.7 is kind of arbitrary. I think, I've heard 1.7, I think it would be safer to say 1.8. Honestly, for polar bonds, that's why I picked HF, of course. I would look for this more than this. This might pop up in a question and ask you to apply this in a question, but I wouldn't hold that 1.7, 1.8, whatever your teacher mentioned as like the thing to look for. I, in a polar bond, look for two different things that are both nonmetals. That, I think, would be where I would look, rather than these numbers. If these numbers pop up in a multiple choice question or a short answer question, they ask you to find the electronegativity difference, then find the electronegativity difference. But I wouldn't hold it firm that like, oh, polar bond needs to be this, needs to be 0 and 1.8. I would look for these two first in a bond. So anyway, we said this was 2.2, this was 4.0, and that's why I changed my number. The difference is 1.8. And that's why I also said it's kind of arbitrary. It's kind of random how some books or some teachers or some professors or some whoever, chemists, define it at 1.7. I think that's kind of arbitrary. I would look for things both being nonmetals to classify something as a polar bond. All right? So look for two different things, and if you have something bonded to its not itself, then you would say that these bonds here, these are polar bonds, because carbon and oxygen are not the same. However, you need to be careful with when classifying nonpolar molecules. So, let's define those two things. A nonpolar molecule has a symmetric distribution of charge. A polar molecule has asymmetric charge distribution. So let me give you the little acronym that helps you remember this, and then I'll go over what this means, because right now you're probably like, what does this mean again? So the acronym that your teachers might have shared with you is SNAP. Symmetry, nonpolar, asymmetry, polar. So SNAP. Symmetry, if the molecule has symmetry, it's nonpolar. If the molecule is asymmetric, it's polar. So the only way I can think to show you what this means is just by showing you a bunch of examples. And I'll go through like pretty much all the ones that you'll probably... First, we'll start with the basic one we did before. FF, F2. Distribution of charge means in a linear molecule like this, and there's only two things bonded, they both have the same electronegativity, which means they both have the same attraction for electrons as the other one. And so since they're sharing these electrons equally, they're both attracting the electrons to themselves equally, we say that it has charge symmetry. So this is a nonpolar bond because both of the atoms are the same, they're both F, and we also say it's a nonpolar molecule because it has symmetry. carbon dioxide. So I'll look up their electronegativities just because. So carbons is 2.6 and oxygens is 3.4. So their electronegativities are not the same. And they're both two different atoms. So C is bonded to something that's not itself on both sides. The O's are not interacting with each other. They're not bonded to each other. So we're not going to evaluate them with each other. We're just going to look at the bonds. The bonds. So C is bonded to something different than itself. So we would say these have polar bonds. However, since, I'm going to redraw it here, since this oxygen is pulling the electrons towards itself away from carbon, and this oxygen is also pulling the electrons away from itself, away from carbon towards itself, they're both tugging equally in both directions. So we would say this molecule has symmetry, which means it's a nonpolar molecule. A real fail-safe method to determine if a molecule is polar or nonpolar, if there's 3 or more atoms, one, look at center atom, look at the one that's in the middle, and the one that's always there's one of, like there's always one carbon in carbon dioxide, there's one carbon in methane, there's one nitrogen in ammonia. Look there. And 2, if there's lone pairs, meaning on the center, then it's a polar molecule. If no lone pairs, again, we were talking about the dots, it's a nonpolar molecule. So if there's 3 or more atoms, look at the one in the middle. If there's lone pairs on it, it's polar. If there's no lone pairs on it, it's not polar. Because you're not going to see too many different examples of polar and nonpolar, because it gets a little gray. But if there's 2 or more atoms, sorry, if there's just 2 atoms. If there's 2 atoms, not 2 or more, just 2. 2 atoms. 1, same atom, like F2, Br2, O2, same atoms on both sides, nonpolar molecule. 2, different, then it's a polar molecule. And I'll go through each example that I can think of. What I might end up doing tonight is wrap up a lot of bonding and then do IMFs tonight, since they kind of go hand in hand, kind of. And then maybe just do periodic table tomorrow as an intro to math. So the videos might be getting pushed ahead a little bit, but I don't really want to rush through everything. And I also don't want to do too much in one video. So math of chem, we'll see what happens. This is going to carry us. I can always take on an extra day if need be. I can always take on an extra day if need be. Anyway, I'm just talking out loud here. So let's do ammonia. And let's practice what we just did. So that's NH3. If I look at NH3, there's 3 or more atoms. If I look at the one in the middle, I see a lone pair. This is a polar molecule. Methane, so CH4. And in case I need to clarify, since these bonds are different, they also have polar bonds. But if you say it's a polar molecule, the bonds are going to be polar every time. Methane, C and H, that's a polar bond. I look at carbon in the middle. I look around it. I see no lone pairs. I see no lonely dots. Nonpolar molecule. Water. Look at oxygen. First, O and H are two different atoms. That's a polar bond. I see lonely dots on oxygen. Polar molecule. So this has asymmetry. This one has, once you say it's this, symmetry, snap. Symmetry, nonpolar. Asymmetry, polar. Symmetry, nonpolar. Polar molecule. Asymmetry, polar. So the key with polar and nonpolar, especially if it's multiple choice, well, really at any point, draw the molecule. A lot of questions would be like, which one is polar? And it would be, or polar bond. Let's do this one. This is a popular one. Which one of the following have polar bonds? A nonpolar molecule. All right. So the choices CO2, NH3, H2, and then H2O. You have to draw these. You just have to. I mean, some of you might be really good at drawing them quickly in your head, but you got 3 hours. Take your pencil or pen and draw these. You gotta draw them out. So, just to recap drawing, you can watch the video I posted on Regents Review 5. That went over all the stuff with drawing. But you gotta draw these out, because some of you might be tempted to put H2. H2 has non-polar bonds. And then you look at the other ones, you're like, they're all different. How do I know if it's polar or non-polar? Take the time to draw them all out. Same thing. Same thing. The thing is bonded to itself. This atom is bonded to the same atom. Nonpolar bond, nonpolar molecule. Lonely dots, polar bond, polar molecule. Lonely dots, polar bond, polar molecule. Bonded to something different. However, there's no lonely dots on carbon. Check. Polar bonds, different atoms, nonpolar molecule. What did that take? 15 minutes already just doing polar and nonpolar? They're hard. Polar and nonpolar is just, it's always a question. It's bound to come up. And it's confusing. I get it. It's really confusing. It's all these words. There's bonds, there's molecules, but the words are the same. And you need to just keep all this knowledge in your head and try to piece it together, because it's all in there. It's in there somewhere. And you just need to piece it together correctly, and it's hard. But you can do it. Take your time. Read the questions. We're at that point of the year. It's almost June. It's getting warm. We want to be outside. We really want to be anywhere that's not school. And I get it. But take your time, read the questions. So many students will make mistakes because they start to zone out. They start rushing through it. Take your breaks. Take a break. Go to the bathroom. Get a drink of water. Just stretch in your chair. Do whatever it takes to give your brain a little minute to just say, okay, focus, focus, focus. It's hard, but you can do it. So, other things with bonding. Stuff I've been noticing a lot recently. So, I don't remember if I did this last video, but I want to cover it again just in case. If I were to look at these 3 bonds, H, O2, and N2. Bonds do not equal electrons. And I've been seeing this a lot recently, especially in the organic unit, because I kind of threw this back at you. I was like, how many electrons are shared in each of these bonds? And for oxygen there, you'd say 2. No, there's 2 pairs, but you got to remember this bond, all of these covalent bonds are sharing electrons that I'm representing here using green. So each of these nitrogens is sharing 3 of their electrons with each other. The oxygens here are 2. The hydrogens are 1. So your bonds are the same as 2 times, your electrons are the same as 2 times however many bonds you see. Just something I've noticed, and a lot of you have been fine doing this, at least in my classes. I don't know. But a lot of you have been fine. But some of us are goofing a little here. Okay. The last part with electronegativity. Again, this is arbitrary, but if it's greater than 1.8, we typically say that's ionic. But honestly, with ionic, I would, again, prefer, if it has a metal with non-metal, I think that is a better indicator that it's ionic than wasting your time looking up the electronegativity difference. Or again, if there's something from table E that's positive with a negative. Some positive ion from table E with some negative ion also from table E, or some negative ion on the periodic table. Other questions you might see dealing with electronegativity is half polar, or you might see with worded more polar. And these are about the bonds here. So this is all about bonds. Which bond is more polar? Which bonds have the greatest ionic character? And all these questions are the same, in a way. You solve them with the same strategy. So let's say the question was, which one of these bonds has the greatest ionic character? And they were all with fluorine. So there was Li with F, Na with F, and K with F. And there'd be a fourth choice, but you'll get the idea. For the more polar bond, which bond is most polar, which bond has the greatest ionic character, you go to the reference table, and you look up their electronegativities. So fluorine I know is 4. Lithium is 1. Sodium is 0.9. And potassium is 0.8. So we go 4.0, 4.0, 4.0, 1.0, 0.9, 0.8. The one with the greatest difference in electronegativity will be the most polar, will have the greatest ionic character. And here, it's probably easy to see. The one with the biggest difference in electronegativity is Kf. And I think that's it for bonding. You're probably like, that's it? It felt like forever. I know. I think that's it. Don't mind me, I'm just drumming over here. Yeah, okay. Let's do IMFs and then maybe call it a night because I don't want to rush through periodic table. And then I also don't want this to be longer than an hour, preferably. And we're already getting dangerously close to 30 minutes. And after I finish IMFs, I feel like we'll have maybe 15 minutes left, and I don't want to rush it. Okay, IMFs. What are IMFs? They are molecular forces biggest thing to remember with these. One, not bonds. These are not the bonds. And it's going to get confusing in a minute because one of the IMFs has the word bond in it, and it's dumb. I hate it. It should just be changed to hydrogen force because they're not bonds. So they're not bonds. And when we talk IMFs, we're really not talking about ionic compounds. Typically, we're going to only be talking about covalent compounds. Now, one of the IMFs, some people might define as an ionic IMF, but usually, when you talk about IMFs and when you see a question about IMFs, it's going to be a covalent compound or a molecular compound, which contains covalent bonds. So, anyway. What is it? So, there's trillions and trillions and trillions. If you take a small cup of water, 8 ounces, trillions of water molecules, an unbelievably high amount of water molecules, and they are attracted to each other. So if you draw water, normally, those dashed lines represent bonds. Those right there. All right, those represent bonds. But there's trillions of these things, like an unbelievably, unfathomably high amount of them. And you might have seen it as 1 mole. There's 6.02 times 10 to the 23rd molecules. So if you had a mole of water, there is that many molecules in a mole. That's huge. You can't fathom that. That's unbelievably big number. So there's a bunch of these in that cup of water. So we're pretending we got a cup of water here, and that's filled with unbelievably high amounts of these. So they're going to interact with each other. So this hydrogen is going to be attracted, not bonded to, but attracted to another oxygen from another water. And that oxygen is going to be attracted to another hydrogen from another water. And this one over here is going to be attracted to some, I didn't leave enough room. It's going to be attracted to some oxygen from another water. And then these guys will attract other oxygens, and so on and so forth. So these attractive forces right here between molecules, not within. So bonds are within, also known as intramolecular. But let's not throw out too many words at you. Bonds are between the atoms within the molecule. IMFs, intermolecular forces, are between other molecules, not within the molecule. And IMFs will help determine your melting point, phases, boiling point, vapor pressure. All this stuff can be determined from IMFs. So IMFs is all about phases. So there's 3 kinds. There's usually only one you have to worry about, but there's dispersion. These dispersion forces are in nonpolar molecules only. Well, they're in nonpolar molecules. They're technically in all. But dispersion you're going to find in your nonpolars. Dipole will be found in your polar molecules. And then the one they always ask about, year to year to year, consistent, almost guaranteed, hydrogen bonding. And we say hydrogen bonding on, you have an H with an F, an O, or an N. You have HF, HO, or HN. Hydrogen bonding is fine. And it's just a special case of dipole-dipole. Hydrogen bonding is unusually strong. Explains water's properties. So a lot of properties about water, like why does it have such a higher boiling point compared to HS and all the other ones below oxygen? And why is it a liquid at room temperature? It's because of these hydrogen bonds, this hydrogen bonding. So I would keep hydrogen bonding in mind. They love to ask about hydrogen bonding. But the other things with IMFs is pretty simple. You want to say stronger. So the stronger the IMF will equal a higher melting point, will equal a higher boiling point, and will equal a lower vapor pressure. And I'll go over what it means in a minute when we take a peek at table H. So, stronger IMF means higher melting, higher boiling, lower vapor pressure. Stronger IMF will, let's say it this way. I'm trying to think of a way to say this. The strongest IMFs will make you a solid. Stronger IMFs, or strong IMFs, will make you a liquid. And then weak ones will make you a gas. Oxygen, you would say, has weak IMFs because oxygen's a gas at room temperature and at pretty much most temperatures. Because oxygen molecules are not very attracted to each other. They're very far apart. So this force of attraction is weak. And this force of attraction is IMFs. So this right here is weak. This attraction is weak. So that's why oxygen's a gas. But if you take something like iodine, I2 at room temperature is a solid. So iodine has very strong attractions. They're very close together at room temperature. They are all attracting each other very closely. So these right here are strong. So the stronger your IMF, the more likely you're a solid. The weaker, the more likely you're a gas. Because the stronger your IMFs, the higher your melting, the higher your boiling, the lower your vapor pressure. So there's a few ways they can throw this at you. They might ask you to use table S and say between these molecules, let's say if you were comparing this whole row, which ones have the strongest IMFs? And you just look at their melting and boiling points. And you go straight down to silicon. Silicon has unbelievably high melting and boiling points. That's huge. That means silicon, compared to these guys, has really, really strong IMFs. And the other ones are pretty strong too. Don't go saying that they're weak. Sodium melts at high temperatures. Magnesium boils at high temperatures. But silicon is really going. Like, it is, really strong. 1687 Kelvin. That's a very, very high melting point. And 3500 boiling point Kelvin, that's hot. That is hot. They might throw you one about table H. Probably bottom 4 of my reference tables. Like top 4 least favorite, easily. It's just random. I think they could save a lot of space, save some page printing by just not having this as a reference table at all and just give it to you in a question. But vapor pressure, first of all, what is that? So, break it down. Pressure of vapor, aka gas. So, I might need to draw this out. Any given moment, if you have a liquid of any substance, it doesn't matter. You can imagine it as whatever you want. These molecules, every once in a while, a few molecules in here, I'll just draw them near the top, they're going to evaporate. Even if it's not at its boiling temperature, they're going to evaporate. Think of a day outside. You see a puddle of water. It's not that hot. Water boils Celsius, 212 degrees Fahrenheit. It better not be getting that hot out there. But that puddle, at some point, gets smaller and smaller and smaller. So liquids evaporate as long as they get enough kinetic energy, as long as they get hit with enough energy, that molecule is going to bounce around and turn into a gas. So some of these molecules start turning into, so this over here is gas. And the pressure from those gases being formed is your vapor pressure. So, logically, a strong IMF will mean it wants to stay as a liquid. And since it wants to stay as a liquid, it does not want to evaporate. So that means it has a low pressure. So a strong IMF wants to stay as a liquid, does not want to evaporate because of these strong IMFs, and therefore has a low vapor pressure. Because if it doesn't want to evaporate, there's not that much gas being formed up there. It's staying as a liquid. So when you look at table H, propanone here has weak IMFs versus ethanoic acid has strong IMFs. Because at any given temperature, let's say 50, there is a whole lot of propanone at 50 degrees. Not that much vapor pressure of ethanoic acid. So there's a whole lot of propanone forming gas at 50 degrees. Not that acid. So if there's a question about IMFs, propanone's weak because it has a very high vapor pressure at any given temperature compared to the other three. Ethanoic acid is very strong IMFs because at any given temperature, even very high temperatures, ethanoic acid just does not want to turn into a gas. Versus propanone, it doesn't even matter if you're at 110 degrees right here. Propanone's pretty much, I'm just a gas. I'm not a liquid, I'm gone, I'm a gas. So, the only other thing, and it came up in the Regents question, what's the boiling point at normal or STP? So right here, that's STP. You might see this word as normal boiling point. Just be careful. At any given temperature, its boiling point is where it hits its curve. So, like, let's say you're at 40, what is this, 0, 10, 20, 40? No, I don't want a highlighter. 40 pressure units. So the boiling point of propanone here would be about 31 degrees. And for, I should have this memorized, ethanol, you would say the boiling point here is about 57. And then for water, 76. And for ethanoic acid, so the temperature scale counts by 5s. This scale over here counts by 10s. So it's 80, 85, 90. But if you see what's its normal boiling point, that just means at STP. And there was one, now and then call it a night, involving, I'm pretty sure it was ethanol. What was its normal boiling point according to table H? And if you follow this dashed line, it's ethanol right there. Sorry, I went up a little bit. It's ethanol. Mr. G, can you draw a straight line? No. It's ethanol right here. Which means you follow this going down. That's 80. Way too many of you were saying 75. This is the June 2014 Regents. Normal boiling point's at 101.3 kPa. 75 hits it at like way lower, under 90. So, I don't know, you guys are being silly. I think that's a good place to stop for tonight. That covers IMFs. I think everything I wanted to cover about IMFs. Let me just check. Yeah, that's it. Excuse me. Woo. I'll put practice problems on my website. It's a great night. You're almost there. Last week was your last full week of school, believe it or not. Unless you're a sophomore taking the global Regents, then it wasn't. I'm sorry.